we're done talking about angular momentum. By the way, let me apologize ahead of time. My Bluetooth microphone is uncharged, so I have to use the built-in mic on this. It might be a little stinky, but it'll still be audible. So let's talk about angular momentum concepts. Now we know that we've been talking about this idea of rotational analogs, and here's a picture of DNA. And, that's the famous double helix. And I know many of you have thought about and studied DNA. And, oh, my goodness, angular momentum all over the place. And it's involved at the atomic and molecular level. So it's pretty interesting. Anyway, the moment of inertia for a single point particle, I equals mr squared. That's the analog of the mass, and r is the distance from that point particle to the spin axis, wherever it happens to be. All right? And the other thing that we did is, we said, all right, you can actually sum up mr squared for every pixel of any irregular object. Get my cursor over here. Like these babies over here. Now, up here is a hoop. The hoop is fairly simple to do without calculus, but all these other babies like the sphere, oh my goodness, you got to do calculus in spherical coordinates, all right? And so it's kind of a pain in the neck. You got to look up integrals and stuff, sines and cosines out the wazoo, but you can do it. These are the results. So for a sphere of mass m and radius r, the moment of inertia, after you do all the calculus, you add up mr squared for every pixel of the sphere. It's 2/5 mr squared. Right now, for a hoop up here at the very top left, it's just mr squared, the mass of the hoop, times r squared. And, the hoop is pretty easy. Every pixel adds up to capital M, the total mass. And every pixel, it's a hoop, so every pixel has the same value of r, which is the radius of the hoop. So this one is just, you don't even have to do any calculus for this. But these other ones you do. Here's a rectangular slab down here, which is good. So here's a kind of a breakdown on like the cylinder. Okay, so what you do is, and by the way, the cylinder here, here's the hoop. And here's the cylinder, and they're the same shape, basically. They have cylindrical symmetry. But the inertia, the moment of inertia here is 1/2 mr squared. Versus for the hoop, it's mr squared, or 1 mr squared. And that factor of 1/2 is significant. Now here's a picture of a cylinder. And what I'd like to point out to you is the following, that the central pixels down near the rotation axis, for instance, for this sphere, number 2 on the left, those all have a relatively small value of r, whatever r is. Okay? So mr squared, gram for gram, is going to be pretty small for those babies. Now out here, the outer layer of pixels in the cylinder, they're going to have a bigger r. It might not, depending on the size of the cylinder, it might not be very big, but, like for instance this. This is a cylindrical object. It's a marker without a cap on it, so it's going to dry out. But this cylindrical marker, the overall radius, capital R, is pretty small. It's like not even, maybe 1 centimeter. All right? But whatever it is, the outer layer of pixels are going to have the biggest r. And so therefore, when you're adding up mr squared pixel by pixel, gram by gram, those babies are going to contribute a lot. And the ones in the middle are not going to contribute as much. Now, contrast that with the hoop. The hoop has all of its mass out there at the biggest value of r. So every pixel has a big r value, and it doesn't have any small values, but the cylinder does. And so when you do all the calculus and trig and stuff, it works out to a factor of 1/2. And if you do the same thing with these other ones, like here's one where you calculate the moment of inertia of something that's a length L about the axis perpendicular to this. This is like a stick, okay? It's 1/12 mass of the stick times the length squared. And here's the interesting thing, and I pointed this out in my annotations a little bit earlier. For all of these simple objects, cylinders, sticks, spheres, hoops, a rectangular slab, the moment of inertia, they have symmetry, so it usually works out after you do all the calculus with that it's dependent on the total mass m, and then the square of like the radius or the square of the length, or in the case of this one down here in the bottom right, a squared plus b squared, the sum of the squares of the width and the height, or the width and the length. A is the width and b is the length of this slab. All right, so it's always and then there's always a fraction in front of it. Now, up here for the hoop, the fraction is just 1. But for the cylinder, it's 1/2. Down here for the sphere, it's 2/5. And and down here, a spherical shell. In other words, like a ping pong ball. Or like an M&M. No, M&Ms aren't spherical. Anyways, a spherical shell, it's going to be a 2/3 here. All right? And it always works out there that way because of symmetry. And no matter how difficult the problem, you guys aren't going to be using calculus very much. But if you were, you would always find one of the major dimensions squared and then the total mass and then a fraction. And if you're doing some kind of, like a potato-shaped object, you'll have the length and the width of the potato, or the length and the average radius of the potato quantity squared, the mass of the potato, and then it might, depending on how irregularly shaped it is, it might be like 0.173 times ml squared or something like that. But there's always a fraction out in front, the mass, and then the square of at least one of the major dimensions. Okay, now Rachel, you had a question.
Yeah, I know you said like big M was the sum of all the masses.
Right.
But what are the masses? I don't get what you mean.
Well, the masses are, just think of each, like this thing over here. Think of the object as being pixelated into a bunch of little teeny cubes or a bunch of little teeny, you can think of it molecule by molecule if you want.
So how would we know how many of them are in there?
Well, if you were trying to calculate this, you'd have to know the density of the object. You'd have to know its length and its radius or diameter. And then you'd have to know where the axis is. Is it going like down here for this cylinder up here? Is it going straight down the pipe, or is it perpendicular to the pipe in the third one here? So you got to know all that stuff. Now you're not going to have to calculate any of these things. Why I'm showing you this is to see the pattern. A mass times a square of a distance, a square of a dimension, or maybe a sum of squares of dimensions, and then a fraction out front, 2/5, 1/2, whatever it happens to be. All right, Austin, did you have a question?
You already answered by saying we didn't have to calculate it.
Yeah, you're not going to have to worry about calculating, but I may give you I sometimes do this with angular momentum. I may give you a table of 2 or 3 of these, with a line drawing of a cylinder, and then the, I equals 1/2 mr squared, and maybe the sphere, and maybe the hoop or something, and then maybe ask you about each of those. You won't have to calculate, because Austin, the reason you don't have to calculate is because to do each of those, to get 1/2 mr squared, you got to do calculus, and that's out of bounds for this class. So, but we can. No, you don't have to memorize it. I'll give it to you on the cover page. If I ask you about this, I'll give it to you on a cover page diagram. Okay, so you'll have to think about it. You'll have to have listened to what I was just saying for the last 5 minutes, and then think about it. And then maybe make a decision in a multiple choice question or two. All right, and there's all kinds of. So think to yourself, what could Dr. B ask about the moment of inertia and comparing them or something like that, or contrasting? You know how like in English class you got to write an essay, compare and contrast, you know, tests of the d'Urbervilles or whatever that is with, you know, some other thing. And same thing here, you can compare and contrast these. Nicole Hauser.
How do you know?
Nicole.
How do you know the value of the fraction? Or like if you were.
You look it up on the table.
Oh, that's it.
Yeah, I mean, if you were in Physics 1, Physics 2048, you'd calculate them. You know, because you need, like I was telling Austin, you got to do calculus. To get that 1/12, or the 1/2, or the 2/5, you got to do a bunch of calculus.
So then, to compare them, how would you know if you're looking at 3 of them?
Well, if I ask you a question about the sphere, look at this diagram. Yeah. And the sphere is nice because any axis that goes through the center of, see, you know, maybe I shouldn't tell you too much because then that means I can't ask you on the test. But for the sphere, any axis that goes to the center of mass is equivalent to every other axis at any other angle because it's spherically symmetric. Now, you can't do that, for instance, up here with the cylinder. This axis that's going straight through the pipe vertically in the third one here is different from this one here. And you get different, and so the fractions are different. This is 1/2, this is 1/12. But any way that you do a sphere, you know, with the axis, you know, this one looks like North Pole to South Pole. But if you go Brazil to China on the equator and integrate or do the calculus, 2/5. You know, it'll always come out. So there's a lot of interesting things about this. But the main thing I want you to remember is a mass, the total mass usually, and a square of the dimension and a fraction. So this fraction over here is definitely smaller. Now, it therefore behooves us to define angular momentum in this way. This is from chapter 10.5, which is the extent of our coverage. And I'll have some more to say about topics in a few minutes. Now, it seems reasonable then, they say, to define angular momentum as L equals I omega. Moment of inertia times, which is the rotational analog of mass, times omega, the angular velocity, which is the rotational analog of, you know, speed or velocity. Right? So P equals mv for regular momentum, angular momentum, I omega. And so that's the way that they do it here. Here's a little... a bigger version of that formula. All right? Now, I want you to think about, go back in your mind to the ice skater demonstration. And let's look at this formula again. L equals I omega. The spin angular momentum. All right, now, Carly started with her hands extended, holding the 2 5-pound weights. And believe me, that's not an easy task. I mean, it seems light, but you hold it out there for a minute and your arm's going to be shaking. I spun her up to a certain angular velocity. Then she brought her arms in to her midsection like this, and her angular momentum, or excuse me, her angular velocity increased. In fact, she felt a little dizzy there, which is a common occurrence. So what changed? Because her angular momentum is a constant. We got good, pretty much constant. You know, we got good bearings on there, so we're not losing a lot to friction. So what changed?
Oh, the distribution of mass.
That's correct. Thank you, Rachel. The distribution of mass. She changed from extension to compression. And so let me ask you again, what changed? What quantity changed? R changed, okay, at least for the two weights. You know, most of Rachel's body, well, her forearms changed a little bit too, and her upper arms, but mostly it's the two weights. So they changed to a very much smaller R. All right. So what did that change in this formula? L equals I omega. Oh, omega. So omega. So bringing the hands in like that. Change. It changes I. It changes the moment of inertia. Okay. So if you now for a human being, figuring out the sum of mr squared for all of them would be kind of tough. All right. But I mean, you could do it if you had to. It'd be painstaking, you know. But whatever it was, you can definitely be sure that this part, the two weights, the mr squared became smaller. What effect did that have on omega? Sped it up. So what happens is this. If you redistribute, what? Yeah, I thought the thing was flaking out on me. If you redistribute the mass and change the moment of inertia, if angular momentum is conserved, which we have, then the spin rate is going to change. Now let's think about Rachel. Okay, let's go back in our minds to Rachel, the first part of the demonstration. She started out with her hands in here, small moment of inertia, and when she extended, she had big moment of inertia, and therefore smaller omega. In other words, she's throwing her hands out like this, slowed her down. All right, and now that's why I call this the ice skater effect. If you look at the Olympics, the figure skaters and stuff, you know, they're out there spinning on the ice, and a lot of times what they'll do, they'll bring their arms in deliberately like this to really speed up. But then when they're at the end of their routine, you know, they finish like this, ta-da, you know. But it's not like, you know. I mean, it is kind of like, look at me, you know, here I am. But it's also to slow themselves down for their spin rate, if they're spinning. So, yeah, the ice skater demonstration. So this is what I call the ice skater effect. And my wonderful students, you better, would you think I'm going to ask any questions about ice skater effect and angular momentum conservation? No? Think again. Okay, question.
You were saying that this kind of concept applies when you have the conservation of momentum, but how do you know when you have that again?
Momentum is conserved if you're on a spinning system of some kind and there's no friction, for instance.
Oh, when nothing is lost.
Right. You know, friction eventually will slow you down, even if you keep your arms all the way in, you know, and then, or keep them all the way out. Eventually, you know, 5 minutes, it will slow down a little bit without changing your moment of inertia. But those are pretty good bearings, and that turntable is designed for this specific experiment. All right, let's talk about another way of look. Oh, question over here.
Okay, so inertia and omega, they're both inverse relationships?
Kind of, that's right. They're inverse relationships if angular momentum is conserved, which is what we have here. Okay. Now, here's another system where we have conservation of angular momentum guaranteed, and that's a gravitational system. The reason for that is there's no angular dependence in the universal law of gravitation. It's all radial. So there's no latitude, longitude dependence. So angular momentum is a conserved quantity. You know, the orbital parameters are basically the radii or the distances and the masses. So here you've got a picture of, you know, low Earth orbit, so that's like the shuttle. And then here's a high eccentricity satellite, then that could be like a spy satellite or a weather satellite, that wants to linger out here at apogee, farthest away from the center of the Earth. It's going pretty slow out here. All right, so that's good for satellites that want to linger over one spot and look at it for a good 3 hours. Because they're going to be, 3 hours out here depending on the, the orbital parameters. And then out here, this might be a geosynchronous orbit out here. And those are usually circular, for a communication satellite. Now, we're going to talk about planets and stuff here in the context of angular momentum states. So let's review here. Rotational analog to F equals ma is torque. And the force changes the momentum state, and therefore torque changes the angular momentum. And the customary symbol is L for angular momentum. And so what that means is that just as Newton's second law can be written delta P over delta T, and this being the version of Newton's law that NASA uses to calculate its rocket trajectories and stuff, the torque equation over here is the change in the angular momentum as a rate of time. So delta L over delta T. All right, so that's the rotational analog to Sir Isaac Newton's second law of motion. So what is changed by the torque? Angular momentum. All right, and there's two kinds of angular momentum. And really it's all one kind, but it's basically two different outlooks. Okay, so you have something called orbital angular momentum, and that's usually the way that we describe the angular momentum state of something orbiting like a point object. So a planet or a comet going around the sun on an elliptical or a circular or even a hyperbolic or a parabolic orbit, we would consider the angular momentum state of that as a point mass with a speed and a distance, all right? A curved path about a central point, all right? Then the other one is spin angular momentum, and that's what we were, messing around with over here. Now that one's basically a bunch of different orbital angular momentums, pixel by pixel, and then streamlining it down into angular momentum equals I omega. Now, let's talk about orbital angular momentum. Question?
On the previous slide, you know that F is the sum of all the forces. Is it also the sum of all the...
Sum of all, yeah, the net force, F equals ma is net force, and the torque equation is the sum of all the torques. So, we're not going to have complex systems where we have a lot of torques. But you know who does? Automotive engineers. You look at a transmission, you think, and guys at NASA. And so, it can get really, especially with torque, it can get pretty nasty. But anyways, orbital angular momentum, let's talk about this. So there's some fixed point of interest like the sun. All right, so that's this greenish yellow ball here in the middle. And there's Earth out on its circular orbit. Or it's nearly circular, so I'll just round it off to a perfect circle. And there's its distance from the point of interest, from the sun. So it has a rotational axis that is going, like from North Pole to South Pole of the sun. All right, now I did draw that in. Next time I use this slide, I might do that. Now, you might also have a comet out on an elliptical orbit. All right, now that's a little trickier because it's on an oblong ellipse. But we can handle that. We've got to do a little trig and stuff like that. So you have some fixed point of interest, and then you have the distance, and just like with leverage, you have to take into account the distance from the object that experiences the force to the center of the force, the sun, and the angle to that point. There's a velocity involved, okay? And so the velocity of Earth, here's the velocity of Earth. It's always tangential to the path. So if you have the orbit, just draw a line in tangent to the orbit. And for a circular orbit like ours, pretty circular, it's perpendicular to whatever the radius is. Okay? Now, for the comet, it's a little trickier. But here's the formula. The orbital angular momentum on a circular orbit anyways, L equals mRV. And the reason for that is there's no trig. On the, you don't have to do any trig on a circular orbit because for every point on the orbit, you have a right angle, Bethany, between the radius and the velocity everywhere around the circle, if you're on a circle. Okay? And a planet on a circular orbit is going to be in uniform circular motion because there's no tangential component to the gravitational force. It's all centripetal. So whatever speed it has at this angle is the same speed it has at every angle around the circle. And so it's perpendicular to the radii, and so it's a very simple calculation, m times r times v. Now that's for circular orbits, and guess what? That also occurs at 2 points on an elliptical orbit, and I'll show you those 2 special points in a second. So you have to take into account the position vector r and the velocity vector v and the geometry of each. Just as with leverage, you have to figure out the lever arm, and what direction the force is versus, the point of application up to the pivot, that line segment, and you know what the angle is with that. So all these angles are important. Question?
What you were saying about, you can just use right angles and everything, that's why it's V instead of omega? Is that what you're saying? It's, even though...
Well, yeah, you can, you know what, omega is V over R, right? So V over R times mr squared is equal to this stuff. So mr squared times omega is equal to this. So it's equivalent. But we think of it in this way because it's an object with mass m and a velocity. But we don't think about the spin, the orbital spin. But here's what we do. But the thing is, Earth is also spinning on its own axis. So we have a 24-hour spin rate for the Earth. 360 degrees every 24 hours. And so 15 degrees per hour. We have spin angular momentum for the Earth. But this is the orbital angular momentum. Okay? All right, now, here's what an ellipse would look like. And you got to use trig out the wazoo for this. Now, Austin, do not get in a panic. You're not going to have to calculate any trig. But I do want to show you what it's about. Now, this is an ellipse. If you remember from high school, semi-major axis, that's half the wide dimension. Semi-minor axis, that's half the short dimension, which is vertical here. And the major axis is horizontal. And I did this out very, very carefully. Eccentricity is 0.8. So here's your comet up here, right? And here's the sun down here. Okay? And this point out here on the comet's orbit, where it's closest to the sun, go ahead and write this down, that's called perihelion. Above the sun, or the point closest to the sun. Now out here, at the far end of the orbit, this is where it's really pokey. Now if this was an Earth orbit, we'd call it apogee. But away from the Earth. But this is a solar orbiting the sun, so we call it aphelion. Away, apo, away. Just like the Greek word for apostle. The apostle is someone that is sent away. Apostle. So the aphelion is way out here. Now, look at that. At those 2 points, the velocity, you're going to have a small velocity arrow over here. All right? And let's say that this thing's going around clockwise. So you're going to have a tiny vertical arrow out here. And guess what? It's perpendicular at that instant of time to this radius vector from aphelion all the way back to the sun. Same thing over here for perihelion. Now here, it's closer to the sun where the gravitational acceleration is bigger, So here, you're going to have, if it's going around clockwise, you're going to have a downward velocity arrow, and it's going to be ginormous. Okay? It's going to be a lot faster. All right? But again, here, at this point, and no other point, the perpendicular, the radius and the velocity are perpendicular. So L equals MRV is appropriate at those 2 points. Now, if you're somewhere out here at an intermediate point, drawing your velocity vector up there, there it is, tangent to the path, but guess what? It's not perpendicular to the radius vector, the position vector. So you got trig out the wazoo here, and since I don't want Austin to start getting, all cranky up and everything, we're not going to do any of the trig. But the level of trig and calculus on this would has made many grad students cry for their mama. So it's tricky. But at these 2 points, aphelion, perihelion, yep, L equals MRV. So you could, if you know something about aphelion or perihelion, you could figure out something about the angular momentum, or vice versa. Question.
What's A, B, C, and E supposed to be?
A is the semi-major axis, B is the semi-minor axis, C is the focal length, and E is the eccentricity. And just go back to your trig book on conic sections, and you'll see what those mean. I just put them in there for reference. I designed this very carefully, so it's a very precise diagram. All right, so the circular orbits are a walk in the park because L equals MRV everywhere. Since velocity is always perpendicular to radius on a circular path. But apogee and perigee for an Earth orbit, perihelion and aphelion for an orbit of the sun, even if it's elliptical like comets, perf, it will work. You can leverage that. Now you can't leverage that on an intermediate point because you got to do trig. A lot of it. But yeah, you can do it. All right. Now, let's get back to angular momentum states, and let's talk about spin angular momentum. Now, we already know a little bit about this. It's the sum of and this is what, I want you to remember. The spin angular momentum is basically the sum of a bunch of orbital angular momentum for each object or each pixel of mass in the object. So again, think of an object as being pixelated, and every pixel of mass is going to have a certain spin rate, omega, like 600 RPM or something. And, electrons and photons have intrinsic angular momentum spin, and we don't really know why that is. But anyways, break up your object into pixels, so like, for instance, like this, take your cylinder and just pixelate it up like this. And then, so for instance, 1 gram of mass per pixel, and then figure out the speed and the distance, where is it? And all oriented to the axle, and then add them all up. Add up MRV for all those, and you'll come out with, this, L equals I omega. It'll be equivalent. So even if this wheel is not moving anywhere, if it's just spinning there, it's got angular momentum, which is kind of an interesting thing. Who would never have thought of this angular momentum concept? Aristotle. He would never have thought of this. Okay, we're getting close to dismissal, so let me do something here with my clicker here. Let me skip. Let's skip over to this one. Let me just conclude with a few exams, a few comments about studying for exam 3. Now, some of you have been asking me, well, Dr. B, what are the chapters and stuff? And somebody has started, Brandon, I guess, a potential list of textbook sections. in discussions. Now, this is the one, and I've already did you notice I commented on it? All right, and they're working on it. And so I want you guys to think about it as something that you can work on too. All right, so here's what it looks like, the second part. So he's got, some of this, and somebody said, well, we actually didn't do much in 6.4, and I think that's actually right. And so I made a somebody said that, and then I said, you're right. Okay, so think of this, Brandon's original post here, and you can see part of it, as the first draft. And just help, the more you guys can pitch in and say, well, on lecture on Wednesday, March, whatever, he did talk about chapter 7 point something, and just add that in. And, by the end of the weekend, you'll have a very good outline. Question?
If you mention something in class and there's a corresponding section to it, should we presume that we need to know all of that section?
The question is, if I mention something in class and there's a corresponding section in the textbook, do you need to read that section? The answer is yes. Okay. I mean, at least the paragraph or so, and I've annotated a lot as well. We're not done yet. I got more comments to come. Austin, do you have a question?
Is there going to be free response like exam 1?
No, it's only going to be multiple choice. Now, another thing that we got going for us is another student, Carly, started an equations page. And everybody's, well, Dr. B, what equations do we need for the... And she's got to start on there. She made a photo, a photo with her phone, I guess, of her notes. But anyways, go in and look at that and use the equation editor and make a nice list and suggest additions. She only got up to chapter 7, I think. But we're going to be going all the way up to chapter 10. But students, don't forget this. We do, as always, in every class, we're doing a lot of skipping and hopping and jumping around. So we skipped over, like in chapter 9, a whole big bunch of chapter 9 after, I think it's 9.3. All right, so keep that in mind. If I don't talk about it in lecture, it's not fair game for the midterm. All right? So these two things will help you really get going. Now, the other thing that I've started working on is the problems I like column on the homework list. I added some in already this morning, and I plan to have a good pile of problems that I like. Also, I'm going to do a talking PDF of homework 7 solution, so you can rectify your homework with that, or rectify your minds with that. Also, I'm going to try to do some problems I like. I might do 2 problems I like on each PDF, 2 at a time. All right, so I'll try to do some of those over the weekend. All right. Now, if you have additional questions, you can come on up to the front. Otherwise, you're dismissed. I'll see you on Monday.